So if you go into Chapter 5 of Blackboard, there will be a template that I'd like you to use. It says PERT CPM template. We really haven't talked about PERT yet, but we have talked about CPM, critical path method. And a lot of times they go together. We'll talk about PERT in a moment. But pull up that template, which is an Excel template. God bless you. Click open. And it looks like this. Now, generally speaking, this is how we use this template. In column A is where we would put the names of the activities. So the first one I think was a prototype. Well, I don't know. I just made up letters, but let's say it was a prototype. And I hit enter. And you see automatically it puts an A to the right, and that's what it'll be known by. I'm going to get lazy with the rest, and I'm going to just call them B, C, D, E, F, G, H, I, and J. And those are our 10 activities. Okay, A through J. Now we need to tell it the three things that our precedence relationship chart did. And the next thing we need to tell it about is the duration. So where we're going to enter duration this first time is we're assuming this first round through that it's deterministic, meaning this is going to happen in 10 days, and we know it's going to happen in 10 days. This is going to happen in 20 days, and we know it's going to happen in 20 days. So we're going to enter it in this column, column F. So activity A is 5 days. Activity B was 7. C is 4. D was 10. E is 5, I believe. F was 15. G is 20. H, is that 10? I is 15. And J is 10. So we've told it about our activities, and we've told it about the duration of those activities. Now the other thing we need to tell it about is our relationships. And we need to give it the node and the predecessor. So A doesn't wait on anything, so I don't have to enter A in here. But I do want to enter, don't put spaces here, don't put quotes, you have to put it exactly the right way. I know it's clunky, it's kludgy, but that's what we have to do. So B, tabbed over, waits on A. Okay. The next one, C, tab over, waits on A. Now D waits on, you see D waits on both B and C. So I have to put both of those in there. So I say D waits on B and D waits on C. So I have to put it in there as two separate ones, not B comma C. D waits on B, D waits on C. E waits on D. F waits on D. G waits on C. H waits on both E and H waits on F. I waits on E. And finally, J waits on H. I think I got everything. So I told her about my nodes, I told her about my duration, and I also told it about the relationships. I kind of diagrammed this through that, that methodology. Now, Believe it or not, we're going to do this with Solver. Well, we're not going to do it. Solver's already set up to do this. What we're going to do when it does is does two passes, just like we did it forward and backwards. The first time, it minimizes the completion time by adhering to the constraints. B has to wait on A. C has to wait on A. Those are constraints, and it minimizes the overall completion time. The decision variables it's deciding behind the scenes are the early start and early finish time. The second time through, it's going to figure out the late start, late finish. Okay, so if you go up to Data and then go to Solver, you'll see, and I don't want you to touch this, don't monkey with it. It already has an objective in there which is hidden right now. It has changing variable cells, it has constraints. So it's doing this as a linear programming behind the scenes. I click Solve, and you're going to be disappointed because it solves it, says finds a solution, but nothing changes. But what it's done is it's primed some things that are hidden here. We can't see them, but if I unhide them, okay, it's primed some things over here, some fields in this template. And if I go over here to PERT output, I'm gonna hit Solver again. So I solved, saved the solution on PERT input, and then I'm going to go to the PERT output tab. Okay, there's two tabs in this workbook, so go to the PERT output tab, and then I'm going to solve on that tab and keep that solution. So what I did is on PERT input, I solved. Okay, this stuff I have over here was hidden. I just unhid it. Yours is probably still hidden. I went over to PERT output and I solved again. And here's the results it gives us. It says, hopefully, exactly what we came up with. And I think we did. We said 57 was the early finish time for the project, right? 57 days. We said A, B, D, F, H, and J are critical. See the asterisks? They are critical. Here are our early start, early finish, late start, late finish, and slack for all of our activities. Okay? Once again, this is better than this. Maybe not. This is a step up from this, I would say. But this is really kind of, archaic as well. Okay? Doing it with this is archaic as well. If you do this in a business platform, you're not going to use this kind of template. You're going to use, like I said, Microsoft Project or Dot Project or Open Workbench. Open Workbench, Dot Project, they're rarely available for free. Okay? They're open source things. You can use it. But this gives us an idea of what this software is capable of. And behind the scenes is a linear program optimization. Okay? So stick with it. The next thing I want to talk about is, if we look at this and go back, a couple of things. I said that I knew this for sure. I said that activity A is going to take 5 days or months or whatever that is. Activity B is going to take 7. Activity C is going to take 4. But just like when Kent drives home, he doesn't know it's going to take exactly 35 minutes. Okay? Normally we don't. Sometimes we do. Sometimes we know, hey, it's going to take 24 hours for the paint to dry, right? We know. It's going to take, I'm not that example, but it's going to take 48 hours is the waiting period for, whatever. Okay? Sometimes it is deterministic, but oftentimes it isn't. Oftentimes it follows a probabilistic distribution. And the one we usually use to classify this is something known as the normal curve or the natural curve or the bell-shaped curve. We've all seen this before somewhere in our undergraduate studies, right? The bell-shaped curve, the normal curve, the natural curve is controlled by two things and two things only. What are the two things that control the natural curve? Two things and two things only. What's the middle of the normal curve? What? You're right, I think so. The mean, right? The mean, the average, right? If this was male height, the average male 59 inches, right? The average height of male is 59 inches. So this is the mean, the middle of the mean. We use the symbol mu to indicate that. That little Greek letter right there, that's mu. Okay, that's the mean, right? Now, what controls how spread out this deal is? What controls how spread out it is? Because me and you could have the same average GPA, but maybe I get 3 A's and an F, and you get straight B's. So there's a different, we both have the same mean of 3.0, but very different distribution. What controls how spread out it is? The normal curve. You said it, Tyler. The standard deviation, right? The standard deviation, you guys have heard of the standard deviation before, yes? Standard deviation controls how spread out it is. The bigger the standard deviation, the more spread out it is. The smaller the standard deviation, the less spread out it is, right? And in fact, there's something called the empirical rule, which we're not going to get into in this class, but about 99.7% of all observations are within 3 standard deviations of the mean. So let's say the average male height, North American, is 69 inches, roughly, 5 feet 9, say. And the standard deviation is 3 inches. Okay? So what that's saying is, if we go over 3 inches of the standard deviation, so about, and you don't have to know this is the empirical rule, about 68% of all males are within 1 standard deviation of the mean. So 59 plus 3 inches is, or 69 plus 3 is 72, that's 56. So 68% of all males are somewhere between 5'6" and 6 foot tall. If we go over another 3 inches, which is 2 standard deviations, 6'3" and 5'3", about 95% of all observations are within 3 standard deviations, or 2 standard deviations. If we go another 3 inches both ways, between 5 feet and 6 feet, this will be 6 feet 6, we have 99.7% of all observations. Okay? That is what the normal curve is all about. And if it's more spread out, that means there's more observations away from the mean, right? If male height had a standard deviation of 30 inches, or let's say 10 inches even, you'd have a lot of giants, more giants than we have now, right? You'd have a lot of 8-footers walking around. You'd have a lot of little people walking around as well, but we don't. No, it's not that volatile, right? It's not that volatile. It controls the spread. Now, how does that make sense when we talk about projects? Well, if you say something is going to take 10 days, and you say it has a standard deviation of, let's say, 2 days. Okay. Well, that would mean about 99.7% of the time it's going to be done within somewhere in the range between 6 inches or 6 days this way and 6 days that way. So somewhere between 4 and 16 days. But if I asked you specifically, what percentage of the time is this activity going to be done 10 days or under? What could you tell me? Since 10 is right in the middle, what percentage of times is going to be done 10 days or under? Right in the middle. Symmetrical. Chris, say it. 50%. If I ask you 12 days or under, you may not be able to give me an exact number, but mathematically we can. It's somewhere about but it's like 64%. Okay. If I ask for 14 inches, it would be higher yet, or 14 days. If I ask before 16 days, you tell me it's like 99.85% of the time. So it can add some probability to projects. We don't just say, hey, it's going to be done in 100 days. We say it's going to be done in 100 days, and the probability it's done under 120 days is 95%. That's what we tell our boss. So it's kind of like hedging our bets a little bit. You know what I'm saying? Realizing that there's risk associated with doing things, that there's wiggle room. It's not always done the same way. Okay? Now, let's say someone has estimated, our project engineer has estimated, that every activity has not only a mean associated with it, but let's say a standard deviation of 1 day. So for each of these, I'm going to add a 1 over here, which is recognizing that this thing, each of these activities has some volatility to it. Does that make sense? Yes? So resolve. So I'm going to resolve over here on the PERT input tab. I'm going to click OK. I'm going to resolve over here on the output tab. I'm going to click OK. And it didn't change a thing except one thing. It now says, hey, our project is still going to get done on 57 days on average, but the overall project has a standard deviation of 2.45 days. So now if I enter into this little box, it's using a function in here that we're not going to learn, but it's called norm dist. If I put in here 57 days, hey, it tells me the probability that this project is going to be done under 57 days is 50% of the time. If someone asks me, hey, what's the odds that this thing's going to be done in under 60 days? I can tell you, hey, 88.9% of the time. And if someone asked me, how about under 70 days, I'm going to tell you, hey, there's a damn near 100% chance of that occurring. If some crazy guy said, hey, what's the odds this thing is done in, I don't know, 50 days, I'm going to say, hey, it's not bloody likely. It's less than a 1% chance, right? 0.002. So, well, basically 0.2% chance of that occurring, given the volatility of these tabs. Okay? So it adds some duration to it. What's the odds this is going to take? What if I asked you this? What's the odds it's going to take, let's use 55 here. What's the odds that it's going to take longer than 55 days? Remember, this gives me the probability it's going to be complete before 55 days. How can I get the probability it's going to take longer than 55 days? Knowing what you know about probability. Right, if it's going to be, if it says 21% of the time it's going to be done before 55 days, the odds it's going to take 55 days or longer is going to be 79%, right? 1 minus it. Does that make sense? So we're going the other way. Now, how often? When Kent told me it's going to take him 35 minutes to go home, if I asked you, give that to me as a probability distribution. Okay? You say mean of 35. What if I said, give it to me as a standard deviation? Mean of 35, standard deviation is what? Okay. You weren't quick with that, right? Because we don't think in terms of normal curves, do we? We don't think in terms of standard deviation. Not many of us. What project management experts have come up with is something that will allow us to bridge the way we think about things to get it in the form of mean and standard deviation. A better way is something called the 3-time estimate approach, which means for every activity, I'm going to put out there 3 times. A, M, and B. And they're not really good acronyms. But A is the best case scenario. M is the most likely. And B is the worst case scenario. Okay? A, M, and B. A is best case. M is most likely. And B is worst case. And what it does is it figures out the average based on what's called a weighted average. The mean looks like this. It says take 1/6 of the best case scenario plus 4/6 of the most likely case scenario plus 1/6 of the worst case scenario. Another way to write that is A plus 4M plus B divided by 6. What it's saying is don't just add up those 3 and divide by 3, because that gives this, the worst case, the best case scenario and the worst case scenario, as much weight as the most likely. So this gives this 1/6 of the weight, this one gets 2/3, and this one gets 1/6. Does that make sense? So we come up with a weighted mean. We still need our standard deviation. Well, the standard deviation is calculated like this. We take the worst case scenario minus the best case and divide by 6. Okay? It's kind of a way to go from the way we think about things. I can tell my son, I can tell my 9-year-old, hey, what's the most likely case you're going to get your homework done? What's best case and what's worst case? And he can give that to me, right? He has no concept of means and standard deviation, right? None whatsoever. Most people are like that. But we can use that basic knowledge, best case, worst case, most likely, to go to a world which allows us to quantify. So what I'm going to do here, whoops, I'm going to delete this. And I'm not going to try to emulate it, but I'm going to say, let's say 2, 5, 7. Whoops. I might have screwed up my thing. 2, 5, 7. Now let's say B has no wiggle room, no deviation. So I'm just going to say that always takes 2 days, no matter what. So 2, 2, 2. Let's do 5, 10, 15. 4, 6, 8, and I'm just going to give them all 4, 6, 8. So if we resolve now, I might have screwed up my template, I'm not sure. No, it looks like it's all right. And then resolve over here. What it's done is it's converted those things to a mean and a standard deviation using those formulas I talked about. And now we have 38 days with a standard deviation of 2.38 days. That method, that 3-time estimate approach, is the basis of something called PERT. PERT stands for, and it's ugly because it came from the military, Program, God bless you, Evaluation, Review Technique. Okay? And really, over the years, project management has developed into one field. So now it's often abbreviated together, PERT /dash CPM, meaning we're going to use the critical path method with PERT where appropriate. Okay, so those are those techniques. So you can see how this is beneficial because oftentimes we don't have an exact, exact time for an activity. We want to factor in that wiggle room, if you will. Okay, factor in some of that wiggle room. Any questions on that? You guys think you can use that template? Okay. I'm going to skip over a couple sections. In this chapter, but the last thing I want to cover today belongs to a family in the project management world called schedule compression techniques. Okay, schedule compression techniques means getting things done faster, compressing the schedule. Getting it done more quickly. There's 2 types of techniques. One type is called fast tracking. Have you ever heard the term, let's fast track that? Have you heard that? What fast tracking is doing things in tandem that aren't ideally done in tandem. For example, when you say you're building a home, okay? A dependency you might have is we want to paint the walls before we lay the carpet, right? because it makes sense, because when you paint the walls, you get paint everywhere and you're going to ruin the carpet, right? That might be the dependency. We have to paint the walls before we lay the carpet. But that's what's called a discretionary dependency, meaning it's not a hard logic dependency. Like I have to put on, when I bake the pizza, I have to preheat the oven before I put it in the oven, right? That doesn't make sense otherwise. That's a hard dependency. But fast tracking is saying, let's get rid of the discretionary dependencies and do it at the same time. Let's not wait for one to be done to do the other. So let's paint and have the carpet guys in at the same damn time. Have you ever watched, a good example of fast tracking, have you ever watched like Extreme Home Makeover Edition? Is that what it's called? You know what I'm talking about? They pull up in the bus, and they have all these guys are in there working like crazy, and they do it like in 48 hours. That's called fast tracking. Things that normally would be done in parallel or in sequence over weeks and weeks are done in a day, 2 days. Okay, that's called fast tracking. We're not really going to talk much about that technique because that's more of a project management technique. The technique, the schedule compression technique that we're going to talk about is something called crashing. And crashing a project sounds bad, does it not? Crashing a project says, hey, why'd you put that guy on my project? Because he crashed it, right? It sounds like a bad thing. But what crashing a project is adding additional resources to the project to decrease the completion time, okay? Completion time, now it makes a few assumptions. Completion time depends only on the amount of money allocated to activities, and reducing an activity's completion time, which is called crashing, I think I mentioned that. There's a couple things we need, okay? We need to look at activities as a normal time and a normal cost, and a crash time and a crash cost. For example, let's say I have activity A and activity B. And let's see, activity A normally takes 10 days. So we're going to say that T sub n, which is normal time to complete it, and its normal cost, let's say, is $1,000. Let's say activity B has a normal time of, let's say, 20 days, and a normal cost of, let's say, $200. Oops. Those are how long they normally take. Now, each of these has a point where I can keep adding resources to it, and it's going to reduce its completion time. So let's say the furthest I could crash activity A down. It can be done in 5 days, but it's going to cost me $2,000, an extra $1,000, right? I can half the time, but I'm going to have to double the money, maybe by assigning 2 people to the job, right? Let's say activity B, it can get done in 10 days, but the cost is going to be, let's say, $1,200. All things being equal, and we don't have all the pictures, all the pieces of the puzzle filled in, but all things being equal, if you wanted to crash this project, which one's a better deal? It's a better bang for your buck. Go ahead. How would we figure that out? Very good. We want to figure out the extra cost for the day it gets us, right? For this one, if we take the crash cost minus the normal cost, divided by the normal time minus the crash time. So this would be 2,000 minus 1,000 is 1,000 divided by 5. This is costing me each day is costing me $200. Each additional day is costing me $200. Does that make sense? So we take the crash cost minus the normal cost divided by the normal time minus the crash time. Gives me $200 per day. Let's do the same thing here. 1,200 minus 200 over, let's see, that would be 20 minus 10. So that gives me 1,000 divided by 10, or $100 per day. So all things being equal, which one provides better bang for my buck? Activity A or activity B? Tyler? B. $100 every day I reduce it. What also matters, though? I don't have that piece filled in this part. What also matters? What if I told you activity B had slack of 50 days and activity A has slack of 0 days? Does that change your mind about where I'd spend my money? Sure. Because crashing this activity, great, it's $100 a day, but who cares? It's not a critical path activity. Maybe I get it done faster, but does it affect my project completion date at all? No. This one, however, the critical path activity, remember when I delayed a critical path activity, what happened? It added it to the end. Well, just think, if I decrease it, it's also likely to do what? Decrease the overall project completion time. So before there was fancy software, this is the analysis that people did. They say, what's the marginal cost for reduction? What's the cost per reduction? And then they started with the critical path activities. That's where they started applying the money, right? Or the resources, the people. Okay? Now there are, and I'm going to show you the templates, but we're not going to use them. Now the software can do this. Okay, now the software can do this. The software can actually do this inside of it. It can say, hey, here's the best way to apply your extra money. Now a couple things. There are activities that cannot be crashed. So sometimes you'll have an activity C that has a normal time of 10 days and a crash a crash time of 10 days. So it can't be crashed. Like the old adage is, it takes 9 months to bear a child no matter how many women you assign to, right? It just is. It is what it is, right? It takes 24 hours for paint to dry no matter how many guys you got working on. Maybe you add blowers, that's adding resource, but still, okay, there's only so much you can do. Now, what we're going to do, no, we're not going to do it, but I want you to think about this. So we're going to look at the marginal cost. And this is an example. The normal cost is $2,000. The normal time is 20 days. The crash cost is $4,400. The crash time is 12 days. So we look at that difference. That's $2,400. 8 days, $2,400. That's $300 a day. And there's something called the linearity assumption, meaning if I add $300, I have to assume I get 1 day. If I add $600, I assume I get 2 days. Now, in reality, we're probably not adding money. We're adding resources. People, labor, right? But it comes down to money. Adding a resource costs money, as you guys well know. The other thing we want to do, okay, once we decide to crash something, is we can look at it two ways. The first way we can do this, and this comes down to the way we think linear program-wise, the first way we can do it is say, we have to meet a deadline. If I think about my linear program, decision variable, if I'm the manager that has to make this decision, I'm trying to decide, I'm just going to put it in English, decide where to spend, or to spend, if I should, the extra money, right? That's what I'm deciding. If I have to meet a deadline, like a good example, Y2K, had to meet that, you guys know what I'm talking about? Some of you are young, but you remember your banking? That was a good time. That was great. It really was. Because I became a valuable resource for a little function of my career. I kid you not. I made I made a lot more. I made more money in those couple years than I made in the next 7 years. Because I had a lot of money. But anyway, decide where to spend the money. Okay, you got to decide where to spend the money. But if we're trying to meet a deadline, where does that go? Does that go in our objective, or does that go in my constraints? If I need to meet a deadline, it's a constraint, right? Subject to done before 12/31/99, right? And the objective then is, hey, we have to adhere to this, minimize the cost, right? And year 2000, the Y2K problem was exactly this, right? We know we had to be ready by 12/31/99. We know a lot of bank software, that's why I worked in bank software, was out of date, out of compliance. They needed resources on it. They spent a lot of money trying to get it up to date as fast as possible because this was non-swappable. Now that's one way to look at it. What's the opposite way to look at it? What's the opposite way? Switch these two things around. Another way is saying, hey, I have X $1,000 to spend, extra $1,000 to spend. So I can't spend more than whatever the value is. I want to spend that money and do what? Minimize the time. Exactly. Okay. Now there's two templates. We're not going to do those in the book because they really are bad. There's one it's called, but if you do an application project, like for the final group project, you may want to take a look at it. Okay? One's called PERT CPM deadline, and that's the one where the deadline is the binding constraint. One's called CPM cost, and that's where the cost. And there's instruction in your book how to do them. We're not going to do them per se. I just wanted to introduce that to you. So that's what craft is, deciding how best to spend our money. All right. Questions on any of that? All right, here's what I'd like you to do for homework for next week then. Get to my Blackboard. Just lost my internet connection. Maybe Blackboard. It's on Blackboard though, okay? It's under, let's see if I can find the book. This is the end of chapter 5. And to do these, you'll use the template for all of them, okay? Use that PERT CPM template. Let's see if this comes back up. Well, you rely on technology, that's what happens. Do number 4. This is on page 312. And number 7. And then when you go to Blackboard, if you're able to get to Blackboard, do those others ones as well, or a couple of the same thing. Okay? But I think 4 and 7 would get you started. 7 uses a 3-time estimate approach, and 4 is just a standard one, the deterministic approach. Okay?
I think it's 4, 7, 8, 8, 8.
Thanks. What is it? 4, 7?
8, 8, 8.
Okay, thank you. Thank you. You got a connection to Blackboard?
No, there's just the one with Blackboard.
Oh, okay.
4 and 7 Blackboard.
All right. You guys have a good week, and I'll see you next Tuesday.